This episode is sponsored by Raycon. Our oceans are a mysterious place, full of strange life bordering on the alien, but what would alien life be like that evolved on an oceanic planet? In some ways our oceans, especially their depths, are almost an alien world, which is ironic since most of Earth's surface is oceans, and life on land is the relative newcomer. There are also some truly strange critters in the deep sea, and some so strange it's been speculated they were alien, and not always as a joke or by a crackpot. Last year we did an episode about life on low-gravity worlds, and folks often ask for a follow-up, life on high-gravity worlds, and we will do that episode, but something I often point out is that there is a very good chance most Earth-like worlds with significantly higher gravity might be entirely covered in oceans, and this may be the majority of naturally habitable worlds in the universe for reasons I'll get into in a bit. It's also a recurring theme in our discussion of aliens, that we might find countless worlds with highly intelligent life but locked beneath oceans, unable to invent technology where fire doesn't exist, therefore evolving no more intelligence than an Earth dolphin or octopus, and who might be stuck on those worlds unless uplifted by some other civilization who is impressed by their brains, and so brings them technology or introduces physiological changes to help them with inventing technology. So I thought today we would ask ourselves what oceanic aliens might be like, what their pathway to civilization might be like, what extra technologies they might need, and what their pathway to the stars is. We'll also explore the possibility that much as life once migrated to land from the oceans, it might migrate back to the sea too, and indeed already has in some cases. Okay, so what do I mean about oceanic plants being more common? Well, first off, water is disgustingly common in this universe. Oxygen is the third most common element in the universe after hydrogen and helium, and it's so reactive that it's almost always bound to another element. Its abundance and reactivity is why oxygen is the most abundant atom in rock. As an example, oxygen is 46% of the atoms in the Earth's crust. Since hydrogen is vastly more abundant in the universe than all rock-forming elements, you can't expect a significant amount of available oxygen to be bound to it in the form of water. Closer to a sun, it is harder to find hydrogen and helium to stick around, and they tend to be blown away, so you can expect to find a lot less water there. The stronger the solar wind, the faster those elements blow away. Solar wind varies by how close you are to a star, but also by the star's type. On the other side of the equation, the more mass a planet has, and the more magnetic field it has, and so the more protection from stellar wind it has, and hence the harder it is for hydrogen and helium to be blown away. A planet's surface area controls how much solar wind it is getting and how thick a given amount of air or water is going to cover it, but it is not linearly proportional to the planet's mass or radius. A planet twice as wide but with the same density would have 8 times the mass but only quadruple the surface area. So if a star with 8 times the water of Earth and spread over only 4 times the area, it would be twice as deep. What's more, it has more gravity and should hold onto its hydrogen much better than Earth did. So it's plausible most worlds bigger than Earth, but otherwise identical, have much deeper oceans. Incidentally, they will likely have a thicker atmosphere too, for the same reasons. The oceans on Earth average a few kilometers in depth. If they were just 1 kilometer deeper, there'd be very little land. There's a lot of assumptions in there. For one thing, Earth's oceans might have come later via comet bombardment after the moon formation event, which would likely have removed all of our lighter elements like hydrogen and helium, given that the event is assumed to have ripped our entire crust off and thrown it into orbit, with much falling back down, some flying off, and some forming the moon. Protoplanet collisions are probably decently common, so Earth might not be an outlier in that regard, and how much cometary matter we get hit with is likely to be dependent on tons of variables to the point of being fairly unique to each system. All in all though, most things I can think of that would tend to factor into a planet retaining water are helped out by being more massive. So too, being farther from your sun helps, and water ice becomes absurdly common once you get into the outer regions of the main solar system. Earth doesn't have much water, strange as that sounds, as our ocean mass is just 0.02% of what Earth does. Alternatively, it makes up a sizable fraction of a lot of the moons of the various gas giants, and our Kuiper Belt contains much more water than the Earth, even though it only masses a couple percent of what Earth does. The Oort cloud beyond that may well contain several entire Earth masses worth of water. Now that isn't necessarily all frozen either, despite being farther from the sun, and gives us another large class of oceanic planets. While there may be many worlds like Earth with open-air water, for each of these there will be many more where the oceans are trapped beneath a layer of ice. It is a peculiar property of water that its solid form, ice, is less dense than its liquid form, and thus floats on top of it. This is true for most types of ice anyway. Some exotic forms like Ice 9 are denser than water. Liquid water that's not under pressure will boil away even at cold temperatures, but ice floating on top of it forms a protective blanket that both keeps the water under pressure and separates it from vacuum on worlds that lack an atmosphere. So we expect to find many worlds, planets or moons, with subsurface oceans beneath thick sheets of ice, and we have a few in our solar system at least, the most well known being Jupiter's moon Europa. This variety of ocean world is going to be very common, as you are pretty limited in open-air water worlds to those of the right mass and location to have them, whereas the presence of liquid water on a gas giant's moon or a dwarf planet is not too dependent on distance from the sun. Indeed, a large moon around a gas giant could also have surface oceans much farther from their sun than a planet could due to tidal heating. So there we have our core cases, worlds with little to no surface land, be they planets or moons, and worlds with a surface of ice. Lots of subtypes in there too, as a world might have shallow oceans all around, what we call an epipelagic world, where the sunlight reaches the ocean bottom in most cases, or the reverse side, what we call an abyssopelagic world, one where the seafloor never rises to within kilometers of the ocean surface. You could also have undersea continents too, islands and landmasses that manage to reach near the surface in some places, but with vast dark gulfs in between. In all cases, for photosynthesis to develop, there would need to be at least a few places where life could get sunlight and nutrients. Without the molecular oxygen provided by photosynthesis, life on these planets would not just have the hurdle of inventing technology without fire, but would likely be unable to form large and complex life. That hardly rules out life, even fairly diverse and plentiful life, but would not be an ideal case for building big and complex food chains. Running on tidal heating or geothermal energy, a species either needs to be far more efficient with its biological processes than we are, or have far fewer middlemen in its food chain than larger animals often have, something that grazed on whatever plants grew around oceanic thermal vents, or squatted on them and grew directly, perhaps like some squid mushroom hybrid that latched onto a vent and drank from it, or engaged in very low-draw energy cycles bordering on hibernation, drifting about burning very little energy till it could catch something or find a new patch to graze on. A lightless world, either because the water is many kilometers deep, or because kilometers of ice block the light, is one where biology is likely to move slowly. Of course, the universe is old, so slow might not matter, and a world of plentiful light but no option for fire might have intelligent critters like whales and dolphins existing for millions of years without inventing fire for technology, but they might well be afforded those millions of years to get smarter too. We often think of civilizations as being on some sort of timeline, but that mostly has to do with technology, and specifically technologies that let you eat up your resources or damage yourselves. A proto-civilization without technology can just keep evolving smarter and smarter, so long as they gain some other advantage to their survival from having their big brains. That's potentially problematic in low-energy ecologies though, because brains are very expensive and need to pay off or they go away. Once you've got technology, that is a good investment, but you need most of that brain first. However, we are still sporting a very similar model on our shoulders to what our ancestors had when they were playing around with bits of flint and tinder, so it had to be valuable to them too. Also, it should be pointed out that a good portion of the smart animals are seagoing. While intelligence is not especially closely correlated with absolute brain size, the title of biggest brain on Earth goes to the sperm whale. Whales and dolphins are renowned for their intelligence, and after mammals and birds, the octopus is often considered one of the brightest. Though we should note that mammals and birds all had land-based ancestors, they and the octopus and some other weird ocean life are good reminders that brain architecture can vary wildly too. The squid, for instance, has a donut-shaped brain, and much of the brains of octopuses seems to be distributed throughout their tentacles, whereas the leech has 32 brains, though they are not clever in partner or tandem. Even the low-energy biosphere issue of sunless environments isn't necessarily a bar on big brains. Spiders have very large brains proportional to their mass, some being fully 80% of their body mass, and they spend most of their time waiting for prey to come to them. There are aquatic spiders like the diving bell spider too, and the basic strategy of the web works as well in water as land. That might be a very good approach for something living in a low-energy environment. Indeed, the sea squirt begins life with a brain in its mobile, tadpole-like larva state, but then plants itself somewhere and absorbs its brain, eyes, and spine as it anchors itself in place for the rest of its existence. Which makes sense. Again, brains are not cheap, and if you're not mobile then they wouldn't seem to serve much purpose, but there may be a lot of in-betweens, and we definitely shouldn't assume nature is divided into stationary plants and mobile animals, flora and fauna, off this planet of ours, since it isn't even neatly divided that way on this planet. Add in alien geology and things might change even more. As an example, for frozen moon worlds, much as we have life that live in the dark mud of the ocean bottom, you could have life forms clinging to the bottom of those ice sheets. Those could be rather mineral rich too, or have pockets of gases float up and cling. They could have upside down frozen ecologies on those. You could also have pockets of gas and liquid inside those kilometer thick surface ice sheets, potentially oases for life, and we do have life-bearing lakes buried kilometers underneath the ice in Antarctica. It's also pretty likely an oceanic planet would have polar regions where ice might accumulate, same as our North Pole, and there is quite a lot of ecology built around those islands made of ice, not rock. It is also not too hard to imagine some organism that melts tunnels through the ice, and those might tend to remain full of gas, some sort of worm or slug eating tunnels through the ice and creating ecosystems behind them in the new space. Indeed, you might have organisms slowly evolve to create very thin greenhouses near the top of the ice by leaving only a tiny thin layer of ice that light could get through. Done right, they could even create small domes and polished ice that act as a system of mirrors and lenses, much like some of the structures we've contemplated building on sun-weak moons and asteroids to create oases under the domes, or long light-filled tunnels bouncing the light around. But that would no longer be oceanic life, so we'll save it for another day, same as surface life that might evolve a thick skin to walk around on those airless moons' icy surfaces. So we've not only got scenarios for alien civilizations of small whales and fish, but also less appealingly, alien super spiders and squid. So there's a pleasant notion in science fiction, giant-brained squid, spiders, and slugs flying through the galaxy. So how do they get spaceships? Well, it would not be as hard for the subsurface oceanic life. Again, they'd probably have options for living in air pockets in the ice, and percolating up to the surface even, and getting off a moon is relative child's play as rocketry grows. Plus, you'd tend to have a lot of other nearby moons to prod you on to colonization, given that all four gas giants each have at least a dozen moons and Jupiter has many dozens. Fuel is also not an issue. They are quite likely to have pockets of methane in that ice, which is a decent rocket fuel. Methane is not only created by many biological processes, but naturally occurs from inorganic processes too. Indeed, it's very abundant on Titan, Saturn's enormous satellite, and we suspect there may be subsurface liquid water on Titan too, beneath its rather dense atmosphere. Methane pockets might be decently common in underwater caverns too. When we start talking about life in water developing technology, we either need some substitute for fire or some plausible way they could have places fire could work and they could be there. Remember, just because we have some underwater cavern with a pocket of oxygen in it that some combustible matter floated into, like driftwood, does not mean someone just figured out fire from that. Waterlogged material doesn't catch fire easily, and humidity would be pretty high in an underwater cavern too, making fire tricky. Humidity is presumably not an issue in an ice cavern, and there's an obvious motive to want fire when in one, but damp material washing into one or getting dragged in would get frozen over, and for that matter, rocks you might light a fire with are likely to be eroded smooth in most cases, and might be hard to make sparks with. It is doable, but it is really iffy if they could discover it. Maybe if they were holding their breath, so to speak, while mining with flint tools in a cave with an oxygen and methane pocket in it. Though you have to survive your pyrotechnic discovery, we do have such explosions in our own mines. There are also some options like electricity or oceanic lava vents as alternatives to combustible materials. We examined some of these scenarios more in our Technology Without Fire episode a couple years back. But we should remember that many technical problems associated with being underwater they can solve by simply creating gas chambers. We ourselves live under a sea of air, and there were quite a few chemistry experiments we couldn't run and things we couldn't invent until we learned to pump air out of small chambers and do certain tasks in vacuum. In fact, aquatic scientists and engineers will probably learn about gas chambers a lot sooner than we came to understand vacuum, because they'll encounter plenty of situations in nature where gas was trapped in a cavern or such, whereas vacuum was something humans had to create before we could do experiments in it. One thing we can say though is that once they have technology, they will probably keep it, even if in some cases they had to rediscover it, same as us. One advantage of a big brain is realizing when something is useful. There is a good chance they'd be smarter than us too. If there is an evolutionary mechanism that tends to favor intelligence, they might just keep getting smarter and smarter till they figure out technology regardless of the hurdles, even if their average person is smarter than Einstein before they figure out how to make steam engines. It makes that notion of giant brain squid and spiders a bit more plausible and horrifying. We can build technology that would work in water, so we have to assume that once they got the ball rolling and are smart enough that they could too and would, even if they had to spend 1 billion years going from the aquatic equivalent of clever monkeys to rocket scientists. Those from surface ocean worlds are a bit disadvantaged on early spaceflight. The subsurface ocean icy moons have it easier than us by far due to their low gravity, but surface ocean worlds are quite likely to have higher gravity and thicker atmospheres than us. And while there is a lot to be said about sea-based rockets, especially some of our jumbo designs like the Sea Dragon super heavy lift rocket design, I would not envy anyone trying to get a space agency running in the sea, let alone doing initial rocket experiments. Fundamentally though, even planets with significantly higher gravity and thicker atmospheres than our own can be escaped with modern rocket technology, and space colonization relies on the assumption that there are much better ways, and such technologies would develop from a deep understanding of universal physical laws. They probably do not absolutely require a progressive process of improving chemical rockets to figure out. Indeed, an oceanic civilization has some advantages with nuclear power, and for that matter such non-rocket launch approaches like mass drivers and space guns have some advantages when you can start them down the tubes deep underwater. One problem they do have is that their ship has to be a pressure vessel able to handle water at whatever pressure they're used to, which might be more than 1 atmosphere, and water is heavy, several hundred times heavier than air, and might require much stronger spaceship hulls too. As an upside, a spacesuit designed to keep liquid water in it rather than air would tend to self-seal from minor punctures icing over, and making something watertight is far easier than airtight. On the downside, especially for a creature used to swimming not walking, trying to move around in a spacesuit full of water on some airless moon like ours, lower gravity or not, is going to be very hard. We often envision uplifted dolphins having some sort of robotic exoskeleton to use for feet and hands, and they might well need something like that to move around their moon. Oceanic life might be much more resistant to G-forces too, and able to accelerate much faster in their spaceships as a result. Space habitats are also potentially problematic. We can achieve gravity by rotating, such as the O'Neill cylinder habitats we often discuss on the show. They can too, but it will be much harder. Hopefully they can handle low or no gravity better than land life might, because trying to create a large 1G rotating habitat full of water is very hard. If they're used to shallow lakes, it's probably okay, but if they are naturally used to living under high pressure, they will need a very thick layer of water in those cylinders, and the stress would be enormous compared to what we usually envision for space habitat landscapes. They might tend to very small cylinder habitats as a result. They will likely need gravity though. Our experiments with fish in space are limited, but the Medaka fish we brought up to the space station, those are the transparent ones, whose insides you can see, which is convenient for research, lost bone mass much faster than humans did in zero gravity. Zero gravity and microgravity are quite rough on life, land or sea-based, and we'll talk about that more next week. Barring all those issues we just mentioned, once they're in space, aquatic aliens have no other disadvantages. Their ships have to be more massive, but that's really only the habitation drum, and we tend to assume that's not the majority of the ship anyway. They might find space living more comfortable too. We often make fun of how often science fiction writers treat space like it was an ocean, but it is more ocean-like in many ways than land-like, so they might be more psychologically suited to space than us. Might have an easier time terraforming or settling too, given that fighting wars with liquid water ought to be easier than fighting wars with land and oxygen-rich atmospheres. Their domes might be underwater vessels or floating rafts instead, and they might need water purifiers instead of air scrubbers, but that is in many ways easier to do than building domes on radiation-scoured airless rocks. In fact, some Earth animals would have tremendous advantages over humans when it comes to space colonization. The African catfish is able to estivate, which is just like hibernating but in warm weather, for up to 4 years in a tiny air-filled capsule encased in dry mud. Once rain returns and softens the mud, it returns to full activity. It's capable of breathing air or water, and thus would not have a problem with a humid, air-filled spaceship. Brine shrimp are animals famously once sold as sea monkeys in the backs of comic books that came in the mail in little packages you just poured into salt water. That was only possible because they can survive complete desiccation for years and return to full health once rehydrated, and conveniently they can also survive extended periods without oxygen. Tardigrades, or water bears, are another example of extremely tough organisms from the sea that might do well in extreme environments to allow life to make the leap to a new and seemingly inhospitable niche, potentially including the near airless and radiation-saturated surfaces of icy moons with subsurface oceans. This toughness is not something we see in larger Earth life, so it might not be possible for larger and more complex organisms. While the technological paths would be harder, they do enjoy some biological options that might be easier. Ocean-world aliens would almost certainly have very good hearing, for instance. Water is much less transparent to light than Earth's atmosphere. Vision is heavily favored for land animals because it allows you to see for many kilometers, but even extremely clear waters one can seldom see clearly beyond 100 meters. Below 4,000 meters, so little light penetrates that sunlight is essentially useless. There would be even less light available under kilometers of ice. In such situations, echolocation can be very useful, but it also comes with some significant drawbacks. For one thing, sending out an echolocation ping reveals your location at least twice as far as your detection radius. For another, the farther you want to see, the more energy you must expend in your pings. But there are advantages too. Echolocation allows you to see through most objects as if they were translucent. If an alien with echolocation looked at us, they would see our skin, but they would also see our bones, lungs, and beating heart. It also might be very handy for finding air pockets and caverns, which might allow fire, but also might be good places to hide. One could imagine a species adapting to be amphibious simply as a means of entering a safe place other organisms couldn't reach. Another non-visual sense commonly used by sea animals is electroreception. This allows sharks and some other fish to sense electromagnetic fields being produced by other living things. Electromagnetic fields are pretty critical to technology too, and if you're naturally able to sense and work with them, you might make rapid progress with electricity and magnetism. All in all, their biggest challenge is just getting to that technological avalanche point of focusing on real science and industry, which we didn't really do ourselves to a few centuries ago. And if they get there in the deep blue sea, then they should be able to get anywhere in the skies above too, as easily as we could. It might take them millions of more years to go from smart to spacefaring, but the universe is many billions of years old, so what's an extra million years here or there? One last thing to consider is that oceanic aliens, be they big spiders or squid or mermaids, might be more plentiful in the universe because there's probably so many more such worlds out there to spawn them. However, we might also find an abundance of water worlds, surface or subsurface, makes many human colonies on them opt to become oceanic themselves. Mermaids might end up as a branch off Homo sapiens, and a fairly common one if such oceanic planets are abundant in the galaxy. We'll get to our schedule and announcements in a moment, but first, a lot of us have had to adjust recently to increasingly mobile offices and conducting business over the phone, or via a phone app for conferences. And if you use many Bluetooth headsets or earbuds, you know how distracting and troubling dangling wires and stems can be, and how important noise-isolating features and a good battery life can be. If you're looking for a good pair of earbuds with noise-isolating features, and about half the price of other premium earbuds, I'd recommend trying out Raycon's Everyday E25 earbuds. Personally, I love them for their snug, discreet, and noise-isolating fit that lets me listen to audiobooks even in a noisy crowd, or when I need to listen on a conference call while taking care of other things. Plus, they've got a good battery life and a very compact charging case with its own battery that can recharge them 4 times while you're on the go. Raycon earbuds give you 6 hours of playtime, seamless Bluetooth pairing, more bass, and a more compact design for a comfortable, noise-isolating fit. Raycon is disrupting the electronics industry by designing premium wireless audio for half the price without compromise. They're doing things differently than other brands out there. From the way they design their products to the way they price them, Raycon prioritizes their customer experience from start to finish. The company was co-founded by folks like Ray J, Snoop Dogg, Melissa Etheridge, and others with comfort, style, and playtime in mind, with a range of colors and style, and Raycon has a 45-day free return policy. Whether you're taking up a new hobby or just want to make your day-to-day life a little bit more comfortable, Raycons are the perfect way to bring premium audio to everything you do, and if you'd like to give them a try, click the link in the description box or go to buyraycon.com/IsaacArthur to get 15% off your Raycon purchase. So we had a last-minute change of schedule, and we'll be switching our last episode of January and first episode of February around. I've been wanting to talk more about colonizing those stars we tend not to think of as prime candidates for planets, and that ended up expanding into a 4-part series that we will be beginning next week with, Colonizing Red Dwarfs, and which we will continue in February and March with the episodes Colonizing Giant Stars, Killing Stars, and Exostellar Civilizations. We were planning to close the month of January out with zero-gravity civilizations, but instead we'll open up the month of February with that, and move on to look at hypothetical dark matter technologies the week after. We are still not done with January though, and again we will look at colonizing red dwarfs next week, then close the month out with our monthly livestream Q&A on Sunday, January 31st, 4 PM Eastern Time. If you want alerts when those and other episodes come out, make sure to subscribe to the channel. And if you'd like to help support future episodes, you can donate to us on Patreon or our website isaacarthur.net, which I'll link in the episode description below, along with all of our various social media forums where you can get updates and chat with others about the concepts in the episodes and many other futuristic ideas. Until next time, thanks for watching and have a great week.